background. Let's get to the motivation for our research. What we are doing is, of course, still fundamental research, but with a clear technological motivation. We are interested in these materials in terms of, or with respect to new possibilities to control and process electrical currents in general, to store and process data. And what I collected here are 3 images. You see on the left-hand side, the IBM Ramak from a little more than 50 years ago. And you see it was quite an effort to move 5 megabytes of information around. You need several people to do so. Nowadays, of course, information storage is so much cheaper. And here's an example of the Toshiba hard disk where you can store 16 terabyte of information. So quite a difference. And this is commercially available for not too much money, enabled by new physics, readout technologies through utilizing the giant magnetoresistance effect and things like that. So there was a huge development over the last 50 years. And for our community in the Ferroelectures, of course, of importance, the ferroelectric random access memory. What I would like to point out now, because I said I would like to bring this into perspective with respect to sustainability, is also how these things are described and our perception of what is important when talking about progress in information technology. For this purpose, I stole from the Cypress webpage this sentence. The next generation ferroelectric RAM memory delivers industry lowest power mission critical non-volatile memory by combining ultra-low power operation with high-speed interfaces and so on. And I think if I would have read this 5 to 10 years ago, this is what I would have highlighted, that we have non-volatile memory, high-speed interfaces, instant non-volatility, and things like that, because that was the focus. How can we push the field forward and get smaller, faster, and better? Today, this is not necessarily the most important. Nowadays, I would say, this is another very, very important aspect. Here, you would highlight industry's lowest power mission critical, ultra low power operation. So you see that other things are now mentioned as well, becoming more and more important also in the funding schemes. And that's why I call this technological progress in a transforming society. We are slowly but surely understand that we have to do things slightly different. And for example, when I just think about how my grandma talked to me about recycling 30 years ago. She was not really believing in recycling plastics, that they do something with it afterwards, we don't know what. And that was a motivation for her not to do it. Nowadays, it is clear for us that plastic goes into a different bin than other trash, and that we have learned to efficiently recycle things. And I have the feeling that we are now at a similar point in material science, that we have to start taking these things more seriously and think into new directions. And this is also, of course, supported politically, and there are huge movements going in this greener direction, for example, propelled by the United Nations and the Agenda 2030 for Sustainable Development. And part of that is are the Sustainable Development Goals, and you see them listed here. The idea is really to bring things forward on a larger front. And if you're interested more in this, I also put the link to the webpage here where you can see and read about the different goals. I think what's important for us is that in all these fields which are named here, material science plays a huge role. So we can have impact with what we are doing. And it's important that we develop new strategies along with new technology so that we don't run into future problems, because we have now the chance to avoid these. And this is exactly what I meant when I said in the beginning, talking about a slightly new perspective on what we are doing. And to bring this, to explain a little more what I mean by that, I stole these nice illustrations from a paper from Alexander King from Iowa State University, who was talking about the increasing elemental footprint. What you see on the left-hand side now is a periodic table where all the elements which were in the Motorola mobile phone in 1983. And these were at that time 35 elements. Nowadays, when we look into our smartphones, 2018, there are 70 elements in the smartphone. You can see already in which direction this goes. It becomes more and more difficult to really recycle afterwards when you play with chemical complexity to induce new functionality. And it's not just the recycling, we also have to take into account where these materials are coming from, so the societal and political impact it may have when we include these materials. Just for comparison, Alexander King is also talking about all forms of life in his paper and compares the periodic table to that. And here you see that it's just 29 elements that are enough to give life on Earth. So we really have to rethink the strategy. As I cited here, the number of elements increases as material science push forward to set new records for key material properties. And this is something we need to consider. How can we functionalize and improve properties in the future for us, mainly in ferroelectric materials, without increasing the chemical complexity? And one possible pathway, which I really like, is to play with defects in the material. The playground we have picked for our research, we cannot solve all the problems, but we have to start somewhere. We looked into controlling conductivity and one step further using ferroelectrics. This is nothing new. A lot of people are going in this direction, and there are many innovative ideas out there how we can achieve these goals. Here are just some examples. One idea is to use the ferroelectric materials, which are usually good dielectrics or insulators, as a template material. And then, as shown in this data set, write conducting wires into the matrix material and play with that. So getting rewritable circuitry at the nanoscale. Another very interesting idea is to use ferroelectrics to build artificial synapses, emulate the behavior we can find in the brain. Here, it's also usually done by combining different materials, building heterostructures, going in the direction of chemical complexity. And another very interesting example, multi-level data storage. This goes in a similar direction, also interesting for neuromorphic computing. How can we use our materials to not just have zeros and ones, but all levels in between to store more information and have more degrees of freedom? Well, the question now is, how can we do so without running into this problem of adding more and more chemicals? Actually, nature is quite smart, and we just have to take a look around how we can generate new functionality without making things more difficult. Actually, we can create, and that's known since 1885, or what was written down in 1885, we can create novel phenomena through symmetry breaking. This is known for a very, very long time and formulated in Newman's principle, which says that the symmetry operations of any physical property of a crystal must include the symmetry operations of the point group of the crystal. If we think about that, we can use this now and turn the whole thing upside down. By changing the point group symmetry, we can create new properties. And what we are all familiar with maybe is that broken inversion symmetry is a precondition to get ferroelectricity. So by changing the symmetry, we can generate new physical properties. And we can get that actually for free. We just have to look into the defect structure a material naturally develops. And there we can find, for example, the 2D domain walls. What you see here is the illustration of a twin wall. And you can see that if I'm an atom sitting right here at the wall, I have a different environment than the atoms sitting in the bulk. Different symmetry, different physical properties. Similar, I can also think about dislocations. Here, we have 1D dislocation lines running through the material. And again, the atoms sitting right at the defect line have a different symmetry environment, can develop different properties compared to the bulk atoms. The nice thing is all this is intrinsically at the nanoscale because we are talking about defect structures at the atomic scale. So it's not just there for free, it is also small, which is what we want for nanotechnology. And we can also go one step further to 0D defects. These would be just natural point defects that occur in our materials. So actually, looking back into Newman's principle, one could say that this is a universal guideline for property engineering via natural defects. So I don't have to add a new dopant, a new element, bring different structures together to engineer the bonds and create new responses at the local scale. And this is what I'm going to use during my talk and give you some examples how these three types of defects can be used to control electrical currents. This is the structure of my talk. As you see already from the title, it's about improper ferroelectrics. So first, I would like to say a few words about improper ferroelectricity and why we picked specifically these materials to engineer the electronic responses. And then I will go step by step through the different types of defects. First, talk a little bit about 2D domain walls and how we can use them to emulate electronic components. Then results we recently got on dislocations, 1D defects, and at the end, talking a little bit about 0D defects, point defects in our material, and the effect they are having. Okay, so let's start with something that most of us will know. If I talk about a proper ferroelectric material, what I have in mind is usually a displacive ferroelectric like barium titanate, lithium niobate, or PZT. These are the textbook ferroelectric materials where I would say they are proper ferroelectrics. The ferroelectricity or spontaneous polarization in this case originates from an off-centering of one ion. In this illustration here, the titanium ion moves upwards. And because of that, the material develops a spontaneous polarization pointing upwards in the left-hand scenario and pointing downwards in the right-hand crystal structure. So here, the electric polarization is really the symmetry breaking order parameter driving the transition from the paraelectric to the ferroelectric state. In contrast, when I'm talking about an improper ferroelectric, the ferroelectricity arises only as a secondary effect due to the symmetry breaking, which is caused by a magnetic or structural order. So this is different. Here, the ferroelectricity is not the symmetry breaking order parameter. It's only coming because of the coupling to the symmetry breaking order parameter. And over the last years, different examples have been established, especially because of the intensive research on multiferroics. That's where people really discovered a lot of materials with unusual ferroelectric properties, and it was kind of a revival of improper ferroelectricity. One mechanism is a spin-driven mechanism that can drive an electric polarization. We will get back to that in a minute. A second one is charge ordering. What's happening here is that we have alternating layers of ions in a different valence state. For example, in the case of lutetium ferrite, iron 3+ and iron 2+, so that we end up with an imbalance and alternating layers with a spontaneous polarization in between. This scenario or this mechanism is one that is still discussed in a little controversially. So I will not go too much into that direction. I will rather focus on the third one, geometric ferroelectricity, where we have geometric transition, for example, in the hexagonal manganites, manganese, oxygen, octahedra, buckle, and tilt, and then lead to a polar displacement of the atoms, causing ferroelectricity. Let's discuss that in a little more detail so that we are all on the same page and you see why I'm so interested in these materials. Let's start with the spin-driven. I just said that in our standard systems like BTO, it's a displacement inversion symmetry breaking that causes the ferroelectric order. So by this displacement, inversion symmetry is broken and we end up with a plus P or the minus P state. In a spin-driven system, we can also have inversion symmetry breaking caused by the magnetic order if the spins order in specific ways. And what you see here is one of the spin structures that can give ferroelectricity, or first break inversion symmetry and thereby kind of prepare the stage for ferroelectricity. You see a cycloidal structure on the left-hand side, this red cross here, that's our center. And when I go from the left to the right along the spin structure, you see that they are rotating in a counterclockwise fashion. We can express that via the spin product and the chirality of the spin structure. And if I now apply the inversion operation, that's what I try to illustrate here, going from the left to the right, you see that the spin, which is yellow on the left, will then change position, go where the blue, the green spin was before, so here, and the green spin will go where the yellow one was before. And when I do that for all spins within the spin system and look again at the chirality, you see it's now opposite. The spins are now rotating clockwise. So inversion symmetry is broken. After applying it, I go from a counterclockwise to a clockwise structure of the spin system. And that can then give me a spontaneous polarization as expressed by this formula, which was first written down by Mostovo in 2006, and it became really one of the most important formulas in spin-driven multifericity. Katsura came to the same results using a slightly different approach. What's important is, and what I would now like to point out, is this one-to-one correlation between the polarization on the left and the spin system on the right. I illustrated that here a little better. So you see that we can have a rotation of the spins, which is clockwise. Polarization points up in this case. We can have a counterclockwise rotation of the spin system so that the polarization is pointing downwards. As I said, one-to-one correlation between polarization direction and spin system. And this also holds at the level of the domain. So we have hybrid domains between with ferroelectric and magnetic order correlated in a one-to-one fashion. So playing with one will also necessarily affect the other. A system where this was discussed in the beginning extensively was terbium manganite, but nowadays we know that this mechanism is really all around. We have it in manganese tungstate, cupric oxide, nickel vanadate, and this list is really very, very long. And it's not just quite unusual mechanism. You can find it in a lot of magnetic materials that have low enough symmetry. The consequences then, I was talking about 2D system and functional domain walls, is that we can get very unusual functional domain wall types in these materials. And I try to illustrate that here. I already mentioned that we can have domains, or that we have inversion symmetry breaking, and we will have domains with opposite chirality. On the left, for example, you have domain 1 with one chirality plus, second domain with chirality minus. And of course, you need to go somehow from the left to the right. Here you see micromagnetic simulations showing the spin system, where you basically see not very much. But if we break that down and look into the chirality, I already said this is a key parameter here. The chirality changes by continuously rotating across the domain wall. But it's not just the magnetic chirality, the polarization has to follow. And there you already see we get a very interesting polarization structure at the domain walls. Even though this is a neutral domain wall, polarization up and down, side by side, it follows the rotation of the magnetic chirality. We get longitudinal Neal components and then charged domain walls in these materials. That is very unusual because this way the system has to do something about the electrostatic divergence, but it leads, as I said, to many functional properties you don't find elsewhere. What we showed in manganese tungstate, for example, is that you can apply in these type of materials magnetic field, and by applying the magnetic field, rotate the magnetic system, and along with that, the polarization direction. So you can play with the charge state of the ferroelectric domain walls, going from neutral to charged back and forth. You can also, for example, use the electrostatic force microscopy or electrical means to switch domains and control the anti-ferromagnetic order that was then in a system terbium manganite. Or you can also use laser-induced switching and control electric or magnetic order and the domain wall structures using light. These are just some examples which arise due to the strong correlation between electric and magnetic order in these improper ferroelectrics. That was just to give you an idea about the added functionality. Let's also look at the other type of improper ferroelectrics, hexagonal manganites with geometric ferroelectricity. Here, yttrium manganite is one of the model systems. What's happening here is at about 1250 Kelvin, the system goes through a structural phase transition, and along with the symmetry reduction, a ferroelectric polarization shows up. What's happening is that these manganese oxygen bipyramids buckle and tilt, and they push the rare earth atom up, or if they tilt in the other direction, it falls down, and we get characteristic displacements that lead to the polarization. Here you see what's happening with the earth atoms. On the left-hand side, you see a out of STEM image. The brighter atoms are erbium in this case, and they show this up, down displacement in between the manganese, which are separating the erbium lines. And the structure can be explained or described in terms of a sinusoidal wave. So the structural order parameter here has an amplitude and a phase. And because of the symmetry of the system, you cannot just have one specific phase. Actually, you can change this modulation by 60 degrees, which is illustrated on the right hand side here. And all these modulations have the same energy. So we do not just have this up, up, down. We can also have up, down, down, up, down, up, and so on. So all these states are energetically equivalent. And you can also see that in this nice data set from Megan and Julia. All 6 states are populated. When you look at order parameter space, we see these red dots here, which illustrate the 6 ferroelectric, structural domain states. And then, as I said, only as a secondary effect, due to the coupling, the polarization comes in because of these structural changes, and we also get a ferroelectric polarization. Here we do no longer have 6 states, we then only have 2 states, and this is, for example, a standard ferroelectric domain pattern which you find in the manganites. The darker regions here would be one polarization direction up, the brighter ones would be polarization direction down, for example. It doesn't look like poor quality. If you look at the year when this image was taken, 1967, you see that this is quite some time ago. So these domain structures and their specific appearance is nothing new. Here, optically, they were already imaged some time ago, but only recently people really got interested in these because high resolution imaging allowed us to resolve these 6-fold meeting points of the domain structures, which you can see all over the image, to look more into the domain wall physics and all the interesting things that are happening in this improper ferroelectric. So this is now another image of the ferroelectric domain structure, now with piezo response force microscopy. Dark means polarization points up, bright means polarization points down. And what you can right away see in this material, even though the polarization is uniaxial, so we only have polarization along the z-axis, the material doesn't really care. The domain walls are meandering around as if there would be no preferred direction. And that's the key point here. We have the structural phase transition that determines the domain pattern. Ferroelectricity comes in only as a secondary effect and has to adapt what's already there. And because of that, we then get, again, very specific domain walls. Before, it was a spin system generating very unusual domain walls. Here, it's a structural order parameter, which gives us, in one and the same system, tail-to-tail domain walls, which are negatively charged, head-to-head domain walls, which are positively charged, or also neutral domain walls here, where we have a side-by-side configuration. So all different flavors, fundamental types of 180-degree domain walls are around, and we can still switch them when we play it right by application of an electric field. So we are also not missing the advantages of normal ferroelectrics, that we can move this around and play with the domain walls and the ferroelectric domains. Okay, so let me briefly sum this up because I brought together a lot of different aspects. What I wanted to emphasize that improper ferroelectric walls are really very interesting functional building blocks. In the spin-driven systems, they are breaking space and time reversal symmetry because of the combined electric and magnetic order. That produces pronounced electric and magnetic couplings, so hybrid domains and domain walls, so that you can use magnetic fields to change the charge state as the ferroelectric domain walls, control them with light, or use electric fields to control antiferromagnetism. So a lot of important cross couplings and functional phenomena can be found here. On the other hand, I mentioned the geometric ferroelectricity, where we have exotic charge states, where we have quasi-mobile 2D semiconductors. I will get more to that afterwards. And in general, unusual electronics at these charged domain walls that we can utilize. To bring this back to the introduction, these are now the 2D systems where we have reduced symmetry, new functional properties because of the specific local environment. And we have not even started to utilize the 1D and also the 0D defects, which we can also use in addition on top of the domain walls, which are around and we can play with. Okay, this is the introduction I want to give. And from now on, I would like to focus on geometric ferroelectricity and what we did utilizing the different defects to control conductivity. And I will start with the domain walls, so the 2D elements which we used to mimic the behavior of electronic components. As I said, it's all about now, it's all about controlling conductivity now. And what I've already shown you is that we have three types, fundamental types of domain walls in this material: tail-to-tail, head-to-head, and side-by-side, which are named with respect to the direction of the polarization arrows and how they change across the wall. The idea now is, if we have different charge states, we can expect different ferroelectric responses, or also different carrier accumulation at these walls. And what we would like to do is use then these different type of walls as different electronic elements that we can then, in the best case scenario, later on bring together to generate more complex circuitry, or control our current. So for example, wall 1 might be used as a gate, another wall may act as a switch, another one as a diode, and if we can wire that up and go towards more complex circuitry, that would be our goal in the end. Oh, sorry for that. That happens when you are I hope we can continue, because I'm not at my place right now. I don't know how I can stop that. Sorry for that interruption. Okay, I was just about to say that we have the different types of walls and would like to emulate the behavior of different components. How are we going to do that? I already mentioned that if we have a ferroelectric domain wall in a manganite, we have the bound charges. When we do temperature-dependent measurements of the conductance at these elements, we see nothing very special in the beginning. What you see is that tail-to-tail or head-to-head domain walls, they all show this the same current temperature behavior, semiconducting properties, which is not very surprising because they're sitting in a semiconducting bulk material. But when you think about it, it's quite interesting, because the colder the material is, the more difficult it will be to bring the carriers to screen the polarization charges. Because if I cool down a ferroelectric, the polarization will still grow. And in our case, it's about 1.5 nanocoulomb per centimeter squared. So we need to screen the increasing bound charges at the walls. At the same time, the relaxation time for the carriers goes down, so we will have really a problem at low temperature to screen the walls. And you can really see that when we do electrostatic force microscopy measurements. We don't see any electrostatic forces at temperatures of 160 Kelvin. When we cool the system further and further down, you see that these lines here are showing up, and at 80 Kelvin, 40 Kelvin, they form exactly this pattern, which we already know from the PFM measurements and the domain walls with the 6-fold meeting points. So suddenly, when I make the system cold enough, I see the strong electrostatic forces from the walls, showing that we are really no longer have fully screened walls. It's not just the effect you can see in electrostatic force microscopy. Actually, you can also measure that same effect with photoemission electron microscopy, showing that it's a universal phenomenon. When you go down in temperature, first, there is no potential difference, and at some point, I see a pronounced potential at the position of the domain walls, because I do no longer screen them. And that's a very important thing, because it's actually one of the rare examples of an unscreened ferroelectric interface, which is still stable. So we have polarization charges pointing towards each other, polarization diverges, and the system still keeps the domain walls. And that's one of the key ingredients which we have to have if we play with the domain walls as electronic components. A secondary effect, because I have head-to-head and tail-to-tail walls, that's what you see here. We measured that back in 2012, is that at the head-to-head walls, where we have positive charges, we see reduced current. Here it's darker than in the bulk. At the tail-to-tail walls, you see bright lines, which means that conductance is enhanced with respect to the bulk. And in between, it gradually changes from insulating to bulk-like at the neutral walls, where there are no bound charges. So these conductance maps, which are collected with a bias tip scanning across the surface and then recording the current, really show you the differences at the domain walls, and that it's driven by the polarization charges. And the wall conductance changes gradually with the orientation of the wall as control parameter. What's happening here is that we have a p-type semiconductor whenever we have tail-to-tail walls, which have negative bound charges, the holes like to go there for screening, and the conductivity increases. At the head-to-head walls, it's the opposite effect. The holes deplete, and we have reduced conductivity. But it can even go one step further. What can happen is that because of the depletion, the conduction band minimum that's shown down here dips below the Fermi energy. And in that case, we have then again an increase in conductance, because locally there's an inversion layer forming of electrons which are sitting there. So when you look at the carrier density and you go towards the wall, it first decreases due to the depletion, where we dip below the Fermi energy. We have enhanced conductance, and you can even see that in local transport measurements. Here you have, for example, one of the head-to-head domain walls. First, the conductance goes down, then up in the middle again, and then down. And this already shows a very interesting, unusual electronic signature of these head-to-head domain walls, which we then utilized. You see that these carriers sitting at the head-to-head walls need a certain activation energy. On the left-hand side, these are now IV curves where we measure the head-to-head conductance, or the conductance at head-to-head walls. They're first insulating all the time, and then when I go above a certain threshold voltage, they become conducting. This is where the electrons, which are sitting at this inversion layer, are contributing to the conductivity. And you can even see in these nice yields measurements from Julia on the right-hand side that at the head-to-head walls, there is a, no, these are not the yields measurements, but this is a result from the yields data, that right at the position of the domain walls, manganese changes the valency going from 3+ to 2.8+, which converts into a certain electronic charge. And these electrons accumulate at the head-to-head walls for screening, and it confirms kind of this bending model that we locally have electrons. And by driving the system with a higher voltage, we can then go from insulating to conducting. What's really nice is we can also do that sitting just with the tip locally on a domain wall, and then going with a current with a voltage up and down, and repeatedly switch between insulating and conducting states relative to the surrounding bulk. Two-state digital switch is kind of the behavior we are mimicking here. And the idea is that we have these electrons which are sitting at the position of the wall. They are in a localized state at low voltages, and when I have a high enough driving voltage, they become itinerant. Another example, which I would like to briefly mention, is the AC properties of domain walls. We can also use the different electronic response at the domain walls to play with the behavior under alternating current. What you see here is is an illustration of the tip on top of our sample. So we are talking about the contact between the tip and the domain wall, which we are now using, which forms a Schottky barrier. That means that we have an asymmetric response of the tip sample interface. And this is different when I have a domain with polarization up compared to a polarization down, which has already been known before, and it's quite trivial. In one case, you accumulate holes at the surface, so you have more mobile carriers. In the other case, you deplete holes at the surface, so you have less carriers. That affects the Schottky barrier, and therefore gives you different conductance at the two domains when I measure it locally. You can also see that when I now apply an AC voltage. So I go plus and minus with the applied voltage and measure the integrated current. You see, one domain is bright, the other is dark, so one is conducting more than the others. What's interesting now is if I ramp up the AC frequency, if I go to higher frequencies, you see that the domain contrast gets worse, and I get more, and I'm left at high frequency with the contrast at the domain walls. So there is one regime when I go to high enough voltages where only the contact with the domain walls has this rectifying behavior. Here you see now up to what frequency that works. So at a frequency of about 10 megahertz, also the domain walls stop rectifying, and you go to symmetric behavior. So sorry, we send in an AC voltage, and what we get out is a rectified current. This is only happening at the position of the wall, so we are really doing this rectification only at the position with the tip and the domain wall. This is controlled now where this drop-off voltage is by the local conductivity. That means that different walls with different conduction also have different drop frequencies. We confirmed that then by doing the same measurements at positively and negatively charged domain walls. And you can nicely see here that the head-to-head walls, which are insulating, and the tail-to-tail walls, which are conducting, they show these drop frequencies, the transition between rectifying and non-rectifying behavior at different frequencies. Another important thing is now that this contact is also voltage dependent. So if you change the voltage, we also have contributions from the interface. The barrier is voltage dependent, so it's not just the conductivity of the wall determining the transition frequency, also the voltage dependence of the interface. And you can see that here, at 0.4 volts, for example, I have still I see no signal in the AC. So the walls are here, have a bipolar response, whereas at 1 volt, you see that we have a strong rectifying behavior. So I can now go to a certain frequency and switch forth and back and play the same game as I already did with the DC current at the head-to-head wall. But what I'm doing here now is I'm switching back and forth between uni and bipolar behavior by changing the voltage we apply to the domain walls. So the electrode wall junction can really be used as to deterministically control the response we get from the walls. To sum up this part with the 2D domain walls as electronic building blocks, what we did so far is we showed that you can control the DC behavior using them as a digital switch, or the AC behavior as active diodes utilizing the wall electrode junction. Then I see that I'm much slower than expected, but let's move on to the dislocations. This is also slightly shorter. We stick with our model system, erbium manganite, and you've already seen this image before, where we have a nice stem image of the erbium atoms and the manganese layers. The only thing I would like to show you here is that these crystals usually have a very perfect structure. Even if you look over larger length scales, we always have this nice layered structure. But what we can do is we can apply an electric field and, as a first glance, ruin this structure. What we did here is we placed an AFM tip, applied 60 volts for 5 seconds, and you see that right under the tip, the structure has changed. How the change looks like, we can see best when we now zoom in, and that's done here. What you see on the left-hand side is now and zoom into the region under the tip, and you see that there is now this dislocated structure. There are the erbium columns which somehow stop and then merge with manganese. So wherever we apply the electric field, these type of defects now occur. Looking at the Fourier transform, you can see that there are now dislocations in this area, which lead to the fact that we no longer have perfect manganese and erbium layers, as you see. Oh, sorry. As you see here in figure C, where we zoom in. This dislocated structure is in fact stable, which DFT calculations showed. It is energetically not too costly. It's about 7 times more than a charged domain wall that occurs in the system. So you just have to put the energy in to induce this dislocation, and then you can stabilize it within the material. And you see that also down here in this sketch, we have the normal structure with the erbium and the manganese layers. Then when we dislocate it by 1/4 along the C direction and 1/3 along the A direction, we get a stable state. So, and the superposition looks very much like what we see in our high resolution images. But if this is true, then we can also do a test experiment and look from the other side, because when we have the DFT structure, it also tells us how it should look when we look from a different direction. And that's what we did to confirm that we have these type of dislocations. You see now we look along the Z-axis of the material, and here we find perfect areas where we have the normal distribution of our erbium atoms. But then in the dislocated structures, we get these double structures. And that's exactly what you would expect when we have the superposition, the dislocated structure here. So that convinced us that we really have induced the partial dislocation with an electric field. But of course, we wanted to control conductivity. And that's why we also looked into the transport properties. And it turned out that these dislocations also have bound charges. And because of that, oxygen vacancies like to sit at these dislocations. The oxygen vacancies induce more N-type carriers in our P-type system they recombine, we end up with less mobile carriers, and that's why the conductivity at the position where we induce a lot of these dislocation drops. And you can really see that when we now put an AFM tip, induce our dislocation or area with a lot of dislocations. At the very center, the conductance or conductivity goes down. You also see that with SEM, so it's not a artifact of the contact. And you see nicely in the cross section, transport properties go down. So by inducing dislocations, another type of defect, we can again play with the transport behavior of our material and thereby change the characteristics at the nanoscale. That were now the 1D defects, and brings me to the last part of my talk, the 0D defects. So in addition to the dislocations, what we also did is we played with the point defects. It's already established that the manganites like to host interstitials, and that you can create interstitials to increase the conductivity. On the other hand, because they are chemically quite flexible, they can also host vacancies, and you can use the vacancies to play with the conductance. This is now a little problematic because both defects are not charge neutral. They will induce gradients and so on. So we thought, why not trying anti-Frenkel defects, so a combination of oxygen vacancies and interstitials to control the conductance. I would now like to first show you how we created them. So we applied an electric voltage to the tip, and you see that only for negative right voltages, we ended up with a change in the current locally where we applied the voltage afterwards. For positive voltages, no change. The changes we induced were up to 4 orders of magnitude. So really locally a very huge change, and they are stable for 2 years and more. This is a huge difference compared to the charged defects I mentioned before, just vacancies or just interstitials. They usually survive only for a few days. Here we are now talking about years. But how did we now show that these are really anti-Frenkel pairs, sorry. Of course, we did a lot of different experiments. We used FIP-SEM cross-section to show that the effect goes several hundred nanometers into the material, not just the surface. We used STEM imaging to show that there is no impact on the crystal structure because the expansion and contraction from the oxygen just compensates. We used EELs to look for tiny features in the spectra to show that these defects are there, and also DFT and MD calculations to show that they are stable. All measurements, all data agreed that there are anti-Frenkel defects, but sometimes the simplest experiment is the most convincing one, and that's what you see here. We just applied the field for longer time and changed the voltage. And I like to zoom in here now. What you see is after increasing for longer time, the dots which we wrote became ring-like structures, which or concentric rings, conducting, insulating, conducting, insulating. And this cannot be explained by just one type of defect. No matter if you have vacancies or interstitials, here it will just expand over time. We need really a model with 2 types of defects to explain a behavior like that, where we can get these conducting and insulating rings. So you need to have 2 kind of defects, and that's what in the end convinced us, together with the stability and all the other experiments, that we are really dealing with anti-Frenkel defects. What's happening now is these anti-Frenkel defects give new effect states, more carriers to the system, so we can really locally write conducting wires into our insulating material and thereby create conducting pathways, which in the best case we can also later on hopefully combine with the domain walls and the point and then the 1D defects to get more complex features. But to wrap up, I hope that I was able to convince you that improper ferroelectrics are a very rich playground for discovering new physics, and that we can really generate unusual electronic responses at the nanoscale by playing with the point defects, the structural defects like dislocations, and the domain walls, and that these defects can really be generated on demand and at the nanoscale. And to bring this now back to this concept of sustainability, why am I so interested in that and see this this connection? Well, the idea here is that we would like to maintain or even reduce elemental footprint. So in the future, it might be a very good way to utilize such intrinsic defects and play even other games than the ones we did. So this was just kind of a proof of concept that these type of defects allow to create functionality to control conductivity, but if you do so in a complex oxide, you can of course also affect the magnetism and other properties. So that's why this, I think, is a very good idea. To not further increase chemical flexibility. And you can also set and reset the structures just by annealing and electrical fields. You can play with the domain walls, the number, and if they are your devices, you can change that. We have the point defects, the very same. You can anneal them and even reset the structures, because at some point your oxygen becomes mobile, and as we've shown here with the thermal annealing, you can reset the structures and get rid of the conducting features. And you can also do that in a slightly more sophisticated way. You can really take your domain walls, which have certain properties. You can functionalize all the area in between by writing these wires, and then by annealing it, go back to the initial state. So here we can really think about resetting and reusing or upgrading the material. And I think that's a very important thing to do right now, way before these things are really matured and could go into a technology. Right now, we are doing the fundamental research, and we have the possibilities to think about problems and possibilities that could create problems later down the road. And it may not even be interesting just for these materials. The structural engineering can be also projected on other material classes where it may help. And I think it's the time to start thinking about this right now. And with that, I'm at the end of my talk, and thank you very much.
Okay, great. Thank you so much. That was fantastic. So please, in the audience, if you can type in questions, and we have time for a few questions. And Laurent Balaiche joins me here as a on the panel, and we can actually put the panel up here. And so great. Let me just start with the I have some yes, I have a question here. Oh, by the way, when you ask questions, please type them in the Q&A slot, not in the chat slot. Just it'll make it a little more straightforward. The question is, can you please, from Alexei Gruverman, could you please comment on potential functionality of domain walls in 2D van der Waals materials where the ferroelectric state can be stack engineered? It's a rather specific question, but are you able to say something about that?
So Alexei was asking about the potential in these materials. Do I understand that correctly?
Yes, yes.
Well, I think this is awesome, because you're, by definition, again, reducing the whole problem by one direction, right? I mean, if you already have your 2D materials, your domain walls become 1D lines. I'm not aware of any measurements so far. Maybe Alexei did them, but then I apologize right now if the paper has come out recently. But I don't know that there are too many papers out there where you really show already the conductivity of the wall, move it around, and that the conductivity moves with the wall. But I think that's a very exciting and extremely interesting direction, because this will allow us ultimately, as he says, to stack that, to go 3D and reduce the dimensions further. But I think there's a lot of work to do. But yes, I mean, I would be very interested in everything that's happening there. Yeah.
Okay.
I haven't looked into that.
Okay. We have a number of questions. So we have a question from Xiaowei Zhang. He just asks, how do you know what's the order of the coupling of the polarization with the order parameter, like whether it couples with q to the third or something like this? I think the answer is by symmetry, but I'll let you answer.
That would be my answer. So the starting point is you look into the point group symmetry of the material. What terms are symmetry allowed when you do the when you look into the free energy, and then you already know, okay, which are the lowest order contributions you can have, and then you start looking at, symmetry is the answer.
Yeah. And of course, by doing that, then you, in the experiment, you can try to figure out what is actually the important order parameter and so forth. So David Vanderbilt asks, regarding dislocations, is the functionality at the 1D partial dislocation, or is the functionality on the 2D stacking faults that span between the dislocations?
That is a question we cannot answer at this point. So when we are doing the conductance measurements, we are measuring an area with a lot of dislocations in there. So what we can measure is that we have a dislocation-rich area and they're only there and not outside, and where we have the dislocations, conductance is reduced. Based on the DFT calculations, we can now extrapolate that this is where you have the oxygen vacancies sitting, and they are affecting the conductance. How much that spreads out and how much every single dislocation contributes, we cannot say on the experiments. So we are integrating over a dislocation-rich area. Yeah, so it could be that they are just disrupting then the path to ground. It could be that we only see that area because with CAFM, when we measure, we are only probing something like 50 to 100 nanometers into the depths. This is something we need to study with higher resolution. Right now, we're averaging. I can just say that the dislocations reduce the conductance, not what an individual one does. I would love to know that, but we have no access right now experimentally.
Okay, and Laurent Belèche has a question. Laurent?
Hi, Denise. First of all, congratulations for the talk. It's really very, very nice. And my question is, in the spin current model, the polarization is proportional to, as you say, the magnetic chirality, Si cross Sj. So what you did, if I understood, you play your magnetic field, affect Si cross Sj, and you change polarization. But one can also imagine the following thing. You flip the polarization by an electric field, and then you control the magnetic chirality. Have you ever done that?
So within the community, when all these experiments were done on the multiferroics, people mainly focused on acting on the magnetic system, because you can apply huge magnetic fields, 10 Tesla, and have that effect. Whereas if you have to go to very high electric fields, usually you may have leakage currents and problems before you switch the polarization. It works both ways, but in most materials, people have studied it the other way around. And because you're also not really changing the angle between the spins, what you're usually doing in systems like manganese tungstate and terbium manganite is you are changing the magnetic easy plane. So you're flopping from, let's say, the AB to the AC plane, and then the polarization follows. So you're not really changing the canting of the spins. I guess that would be again another order of magnitude when you look at the magnetic field for doing that. You're just flopping the easy plane, and that's how the polarization follows, and you get this 90-degree rotation.
Great, great. So I have a question about stability. So you did mention it, and it seems like for applications that's going to be a key issue. I guess there's like a million systems that one could look at, but so I guess some of them may the defects may be more stable than others. Is that some? I guess that must be. I guess my question is what's being done to try to improve the stability or investigate the stability of the structures for long-term applications?
So you're now specifically referring to the point defect, the anti-Frenkel?
Well, actually, I'm referring to everything. So all of these defects, they have to last in order for. I mean, normally we think, at least I traditionally would think of domain walls as being something quite fluid. But and if you apply a field or something, they move, or even just in temperature, they may move. But is it possible that you just need a certain density of defects, or do you really need the specific defect to stay there in the right place in order to have a reproducible?
Well, I would of course like to have one defect in one place all the time. This is but that's exactly the beauty of the improper ferroelectrics. So when I have now my domains pattern in the manganites and I would like to switch it, you really have to go to low temperatures and apply huge electric fields so that you even switch the system, because we are acting on the improper, the secondary order parameter, and you have to kind of drag the structural change along with you. So they are extremely stable, and you have to apply at least one order of magnitude higher electric fields than what we are working with when we play with the conductivity.
Oh, okay, great.
So the activation of the currents and the movement of the domain walls are really far apart. That's a bigger problem with the proper ferroelectrics. There, people usually use the domain walls, they create them and erase them in between electrodes to control conductance. So there you don't want them too stable, so you can write and erase them. We want them to be stable because with the point defects, it's the same with the anti-Frenkel. Since they are charge neutral and screened, they can last on much longer time scales than just the charge defect, which will somehow interact with the environment. So there I cannot say too much about the details. We're investigating that right now, how we can drive them apart and really control where they're sitting, avoid or induce recombination of the defects. From the data shows we can have them for 2 years. If they don't see each other, that is reasonable because there are also energy barriers for recombination. But the very details at this point, it's a proof of concept. So we are still trying to figure out how far we can go with that.
Okay, we're going to have one last question from Ganesh that I'll read in just a second, and then I'll just wrap things up with discussion of the remaining schedule of the series, and thank Denise again for a really excellent talk. So Ganesh asks, do the point defects change the carrier density of walls like in a doped semiconductor, or do they actually change the structure, like changing the polarization structure and thus the charge in the wall?
Sorry, can you repeat that again?
Yeah. So he asks if the point defects are like doping in a semiconductor, or are they actually changing the polarization structure?
So we don't, with the resolution we have in the images, we don't see any displacement of the atoms beyond what we see anyhow for the polarization. So within the resolution, no change. So they're really hidden, not visible defects. That's why we also had to try all the different techniques to see the effects, because I think a vacancy causes in the manganites an expansion, an interstitial a contraction, and so the effect on the lattice compensates. It must be there, but if you have both sitting 6 Armstrong away from each other, we don't resolve that. So that's why it was so hard to track it down.
Okay, fantastic. So let's all thank Professor Meier again, and let me just give a short mention of the continuing series. So our next talk will be August 12th by Daniel Sando from Australia on super R bismuth ferrite epitaxial stabilization of a low symmetry phase with enhanced electromechanical response. And I want to mention that I want to thank our organizing committee who's been helping behind the scenes: Laurent Belage, Sari Stryer, Jorge Iniguez, and Beth Nowodnik. And I also want to mention that, we are planning to have on February 6th to 9th, 2022, an in-person workshop, the 33rd workshop on fundamental physics of ferroelectrics. And if you're interested in being involved in planning, you want to be a local organizer, you have a good idea of a location or a venue, we need to settle all this pretty soon. It's like 6 months away. It's about time to do this. So please contact me if you have any ideas about this. Looking forward to that as well. So thank you all for participating. We had a good turnout, even though it's vacation season, so that we're about 70 plus people here today. So that's great. And so thanks again, and we'll say goodbye. So bye-bye.
Thank you very much, and goodbye.